Okay, so implicit differentiation, trying to do this in a nutshell. Why do we do implicit differentiation? Well, so far we've just restricted ourselves to cases where y is a function of x. But if y was not a function of x, what would we do? Well, what we would do is implicit differentiation. So how does this stuff work? We're pretty much going to differentiate just as we did before, but whenever we take the derivative of y, we're going to throw a dy dx after that. And when we do this for a lot of things, we're going to end up with a hot mess. So can we leave it as a hot mess? Of course not. We must clean our mess. And how do we clean up our mess? We're going to solve the equation we have for dy dx. Once you do this, once you finish taking the derivative, what you're left with is a big, ugly linear equation, and this is the variable that you're solving the linear equation for. Naturally, they're going to end up giving us some application problems, or find the equation of a tangent line at a point, things that they ask us to do before with derivatives. And how do we proceed moving forward? Just like we did as before. We will get an equation for the derivative. We apply it just as we did before. So a couple quick examples. This one is one that they used in the book. Find the derivative of y with respect to x if we have the equation y squared equals x. So y is definitely not a function of x here. So for our solution, what do? We take the derivative of each side. For our left side, we're going to use the power rule. And since we're taking the derivative of y, we're going to throw in the dy dx. The derivative of x is just 1. So we have that, but we are not done. We're done once we have it solved for dy dx. It's getting multiplied by something, and we get rid of a multiplication by dividing the thing away. So we divide each side by 2y, and now we get dy over dx is 1 over 2y. That is our derivative with respect to x. If this was an application problem, this is what we would use moving forward. Another example, this one wasn't in the book. So what if we had a function, or what if we had the equation sine of the product of xy equals 1/2, and we wanted to take the derivative of that with respect to x? Well, we're going to go ahead, take the derivative of each side. The right side's going to be great, it's a constant, and the derivative of a constant is 0. 0 is the derivative of a constant. But for this side, we got a couple things going on here. We're going to need both the chain rule, because there's something going on inside the sine function, and what's going on inside the sine function is a product, so we will need the product rule. So for the chain rule, the derivative of sine is cosine. So there was our turkey, and now we got to take the derivative of the stuffing, and the stuffing is a product. So first times the derivative of the second plus the derivative of the first times the second. And these are nice and pretty neat. The derivative of y is just going to be 1, but we need the dy dx. The derivative of x is 1, and then we got the y there. So that's where we're at right now, but we're not done until we've got this solved for the dy dx. So to do that, we're going to have to distribute our cosine of xy across the board, and then start isolating the dy dx. So we do that by subtracting away this other term from each side of the equation. That'll give us that, and we can get rid of everything that's multiplying the dy dx by dividing it away. Our cosine of xy is going to end up canceling each other out, and we're left with the derivative of y with respect to x is just negative y over x. So that's a pretty surprisingly basic derivative given the ugliness of our original function. But such is life. So hopefully this is everything that you need to get started as I look through the rest of the examples in the book. This is the main part of it, and again, what happens after that with most of the examples in the book? If they ask you about this stuff, we get our derivative as we did before, which is solving for that, and then proceed like we did before. So hopefully this is enough to get you up and running.